Working numerically, we've seen that the function c equals x squared y squared plus square root of y sine x in the vicinity of the point pi over 2, 3, changes at a rate of approximately 28 units for every unit change in the x value, and approximately 16 units for every unit of change in the y value. Giving rise to this picture where we start at the point, let's clarify this, this would be our point pi over 2, 3, 0. We get a function value of 270, which is the distance from the xy plane up to the graph point. And that point is pi over 2, 3, approximately 270. Remember, the 270 is a pretty bad approximation, so don't take that too literally. So that's the coordinates of this point. If we move 1/10 of a unit in the x direction, then, since the rate of change of x with respect rate of change of f with respect to x is 28, we expect that by moving 1/10 of a unit here, we'll move up 2.8 units. Moving 0.05 units in this direction, we expect that because of the slope in the y direction, the y partial derivative, our delta f is going to be about 0.8. So that delta f due to the delta y, due to the change in y, is about 0.8. Delta f due to the change in x is about 2.8. Now, geometrically, again, let's look at this rectangle, and let's let this be the point pi over 2, 3 in the xy plane. So let's just, okay, say we've got the xy plane here. Here's the x, here's the y, and starting from this point, okay, here's the y and here's the x. Starting from this point, if we move 1/10 of a unit in the x direction, so we move over 0.1, and I'm exaggerating that distance, and if we move 0.5 units in the y direction, that's going to move us over to this point. Now, this point is the pi over 2, 3. This point is pi over 2 plus 0.1, 3.05. By moving 1/10 of a unit in this direction, x went up by about 2.8 units. The value of our function went up by 2.8 units. Moving 0.5 units in this direction, our function would go up by about 0.8 units. This is assuming that the rate of change doesn't change much over this small region. So assume small changes in fx and fy in the region of the small rectangle we show here. In other words, you got a small rectangle, 0.1 units by 0.5 units, corners at pi over 2, 3, and pi over 2 plus 0.1, 3.05. If we were to evaluate fx and fy at any point within this region, we're assuming that the value of fx, the partial derivative with respect to x, won't vary a lot from 28. Fy won't vary a lot from 16. If we make that assumption, then the change that we would have between here and here as we move from y coordinate 3 to 3.05 along this side of the rectangle will be about the same as it would be along this side of the rectangle. Geometrically, that means if we complete the rectangle up here, our change in y and our change in x will be similar on this end of the rectangle and on this end of the rectangle to what they were here and here. If that's the case, then the total change in F as we move from here to here should be our sum of 0.8 and 2.8. If we go from here to here, we expect F to change by about 2.8. If we go from here to here, we expect the change to be about 0.8 because it should be about the same as it was over here. As we change Y, we get about the same change, whether we're here or here. So that the total change in F should be about 3.6. Our situation is therefore depicted a little larger, as we see here. First of all, f of x, y, z is approximately 270 at this point. F is changing at a rate of approximately 28 units per unit of x motion, 16 units per unit of y motion if we move along, if we move in the neighborhood close to this point. Now let's assume that we got some region here. This is a small region near the point our point was pi over 2,3. Didn't label that. But if this is some small region near pi over 2,3, what we're saying is that fx stays reasonably close to 28. Fy stays reasonably close to 16. Through the entire region. That means that as we move from here to here, F changes by about 2.8 due to our change in x from here to here, delta x being 1. And as we move from here to here, F changes by 0.8 due to the delta y. And that's as we move from here to here. I should have drawn this rectangle a little bigger so I could write that in a little more clearly. Now, if f changes by about 2.8 as we move from here to here, that tenth of a unit, well, we have a tenth of a unit here also. And in moving that tenth of a unit in the x direction, if our fx stays reasonably close to 2.8, then f should change by about 2.8 as we move from here to here. And as we move from here to here in the y direction, the fy is going to stay, if the fy stays reasonably close to 16, we get about the same change in this direction. So that we can draw this rectangle just a little bigger. Delta F equals fx delta x should be about 2.8, where this distance is 0.1. And here, delta f, which is fx delta x, should again be close to 2.8 as we move from here to here. And the delta F equals Fy delta Y is approximately 0.8 here, and delta F would be approximately 0.8 here. To the extent that Fx and Fy stay close to the values they have here, these approximations will work, which means if we move from here to here, F goes up by 2.8, and if we move from here to here, F goes up by 0.8. Now, I'm using delta F for the change in F along this line and change in F along this line, and also the change in these opposite directions, and I've got two different numbers that appear to be equal to delta F. I'm having a little problem with notation here. I don't want to call this delta Fx because then it looks like the partial derivative. Don't want to call it delta F1 or delta F2. So let's just keep in mind that the notation here is a little bit sloppy. But I can say that delta F total as we move from this point to this point is approximately 2.8 plus 0.8, which is 3.6.